Welcome to the deep dive. Today, we're plunging into something really foundational, the very origins of an idea that, well, it underpins so much of modern artificial intelligence.
Right.
Yet it started with this observation about our own brains that sounds almost deceptively simple.
Mm.
It's a phrase you might have heard maybe bouncing around in talks about neuroscience or AI. Neurons that fire together wire together.
That specific phrase, yeah, it's catchy.
It is. And it's this elegant way of saying how our brains learn, how they adapt. And somehow that became the bedrock for a whole field of computer science.
It's fascinating, isn't it? How this fundamental biological insight from back in the mid-20th century,
Way back.
it laid the conceptual groundwork for these incredibly complex AI systems we're interacting with every single day now.
It really is like a bridge.
It is a bridge between the wetware in our heads, our organic brains,
Right.
and the digital circuits in our most advanced machines. It just highlights this deep, sometimes really surprising synergy between biology and computation.
Exactly. And our journey today, it really starts with one person, a brilliant mind, the Canadian psychologist Donald Hebb,
Yeah.
and his groundbreaking 1949 work, The Organization of Behavior. This book, in so many ways, it was just way ahead of its time.
Truly ahead of its time.
The kind of glimpse into how learning might actually happen, at a cellular level, long before we had the computers to really even try and mimic it properly.
Right, the tech just wasn't there.
So for this deep dive, our mission, if you like, is to
Yeah.
trace how that biological insight became the fundamental principle for artificial neural networks. We'll go from early psychology and neuroscience through those decades where, well, people either misunderstood it or just couldn't build it computationally.
The so-called winter.
Yeah, exactly, the AI winter.
Yeah.
Right up to the complex, deep learning systems that are, let's face it, reshaping our world right now.
It's quite a story.
It is. We're going on a journey, basically, from the brain's biology to the silicon chips that are trying to copy how it learns.
Yeah.
So what does this all mean for you listening, for anyone curious about the why behind AI's big moment now?
Well, I think it means understanding the deep roots, the often overlooked origins of AI's power, its amazing adaptability.
It's understanding where it all began. Okay, so let's really unpack this core idea from Hebb. Neurons that fire together wire together. Like we said, sounds almost like a catchy slogan, maybe a nursery rhyme.
It does have that ring to it.
But the implications are just massive for how we think about the actual mechanics of learning, of memory. Can you break down what Hebb was really getting at?
Yeah, it's a great summary, a really elegant one of a pretty complex biological process, and honestly, it's kind of a Blinkist-level takeaway that's really held up over time.
Right.
Hebb's core hypothesis, the thing that gets boiled down to that phrase, is basically this. When one neuron, let's call it neuron A, repeatedly or persistently helps to excite another neuron B, some kind of metabolic change happens in one cell, or maybe both. And the crucial part is, this change makes neuron A better at firing neuron B next time. It increases the efficiency of that connection.
Oh, so it's like paving a path.
Exactly. That's a common analogy. Think of a path in a forest. The more you walk it, the clearer and deeper it gets.
Easier to follow next time.
Right. The more these two specific neurons talk to each other, the stronger that connection becomes. It makes it easier for the signal to pass along that specific route. It's like learning physically embodied experience, literally reshaping the brain's wiring.
Wow.
The really profound thing Hebb proposed was that learning isn't just some abstract thing floating around, it's tangible. It's happening right there at the synapse, the connection point.
So it's not just that individual neurons are firing, it's the timing, the firing together that creates this lasting physical change, this connection strengthening.
That's the key, the contingency.
It's almost like the brain is constantly editing its own circuits based on what it experiences. So what was so revolutionary about that specific idea back then, given where neuroscience was in the 1940s? And how did this model of associative learning connect with or maybe challenge other ideas floating around?
Well, it was revolutionary because Hebb provided a plausible mechanism for associative learning. People knew learning happened, obviously, but the how at the neural level, that was much, much fuzzier.
Right.
His idea naturally suggested the concept of cell assemblies. Think of these as groups of neurons that tend to fire together because they've become functionally linked through this wiring together process.
Okay, so not just one neuron, but a whole team.
Exactly. A team or an assembly, and this whole group firing in a specific pattern could represent a thought or a memory or maybe a concept. Like When you think of your grandmother, it's not just one grandma neuron lighting up.
Right, that seems too simple.
It's likely a whole distributed assembly of neurons, ones linked to her face, her voice, memories associated with her, all firing in concert. And the beauty is, these assemblies aren't fixed. They can be dynamic, they can overlap, like how thinking of apple might activate parts of the assembly for red or fruit.
And maybe they're robust, like if one neuron in the assembly dies, you don't completely lose the concept.
Precisely. The pattern can often still be completed, just like you can recognize a familiar face, even if part of it is obscured. It's a very powerful idea for how the brain could store and retrieve information in a flexible, resilient way.
So the brain is kind of organizing itself into these complex functional circuits based on repetition, based on experience, building these little task forces for every concept or memory.
That's a good way to put it. And this connectionist view, it fits really well with the adaptive nature we see in biology. Think about critical periods in development.
Oh yeah, like with language learning.
Exactly like language learning. During these periods, often when we're very young, the brain's networks are incredibly malleable, like sponges soaking up information.
Right.
Synaptic connections, those paths we talked about, they get strengthened or weakened based heavily on the sensory input, the experiences the child is having. This shapes the brain, leading to these characteristic response patterns.
So if a child hears a certain language constantly,
The neural pathways for processing that language get strongly reinforced. The sounds, the grammar, the rhythm. If a child, tragically, isn't exposed to language during that critical window.
it's much harder or maybe impossible to become truly fluent later on.
Right, because those specific pathways just didn't get formed and strengthened in the same way. It really highlights the brain's incredible ability to wire itself based on activity, based on experience. It lines up perfectly with Hebb's core idea. It's not just what we learn, but when and how intensely those neural circuits get exercised.
That example of critical periods really drives it home. Makes the whole Hebbian concept feel so real, so tangible. But while neurologists were grappling with this, were there others, maybe outside pure neurology, looking at complex human abilities that sort of foreshadowed the challenges AI would later face? Problems that these learning networks would eventually try to solve.
Oh, definitely. Think about someone like Norbert Wiener, a pioneer in cybernetics. He wrote about the challenge of pattern recognition, something we humans do almost effortlessly, but which is incredibly hard to program.
Like recognizing a face.
Recognizing a face, or even simpler things, like identifying a circle. Is it a big circle, a small one? Is it tilted, so it looks like an ellipse? Is it close or far? How does a system recognize the essential circleness regardless of these variations?
Or seeing shapes in clouds. That's another classic one.
Exactly. Seeing faces or animals in random cloud formations, that requires pulling out meaningful patterns from, essentially, noise. It demands the ability to extract invariant features, the core essence of a pattern, despite all the variations in how it appears.
And those are precisely the kinds of really hard problems that artificial neural networks much later would be specifically designed to tackle, right?
Absolutely. Wiener wasn't talking about synaptic plasticity directly, but he was highlighting the functional need for systems that could generalize, that could abstract meaningful information from messy, variable sensory input. That's a core function that Hebbian-inspired learning ultimately aims to achieve. The big insight there is that generalization, recognizing patterns across countless variations, is a hallmark of intelligence, whether it's biological or artificial. And it set a benchmark for what AI would need to accomplish.
Okay, so Hebb gives us this foundational biological idea, a potential blueprint for learning in the brain. It's powerful stuff. And naturally, people started thinking, hey, can we build machines that learn like that?
Right, the engineering impulse kicks in.
Exactly. And that intellectual leap led to the first attempts at artificial neural networks. What did those early models look like? How did they try to, capture Hebb's vision in silicon or whatever they were using back then?
Well, inspired by Hebb, these early models tried to mimic brain function, but in a very simplified way. One of the most famous and definitely influential early on was the Perceptron.
The Perceptron, right.
Yeah.
Developed by Frank Rosenblatt?
That's the one, Frank Rosenblatt, late 1950s. The Perceptron was really one of the very first artificial neural network models. Its basic job was classification, usually binary classification, deciding if an input belongs to one category or another. a yes or no kind of decision.
Pretty simple, fundamental.
Fundamentally simple, yes. It was a single-layer network. It took several inputs, multiplied each by a weight. Think of that as the connection strength or importance.
Okay.
Summed them all up, and then passed that sum through a simple threshold function. If the sum was above the threshold, it fired, outputting a yes or a 1. If below, it output no or a 0.
And how did it learn? Did the weights change?
Yes, that was the key link back to Hebb, conceptually at least. The idea was that the weights would adjust based on whether the perceptron got the classification right or wrong. If it was wrong, you'd tweak the weights in a way that made the correct answer more likely next time, gradually strengthening connections that led to success. It was the first real, concrete attempt to implement something like Hebbian learning computationally.
That sounds like a fantastic start.
Right.
Really capturing that spirit of neurons that fire together, wire together in an artificial way. Seems like it held a lot of
It
promise.
generated a lot of excitement initially.
But then the story takes a turn, doesn't it? It's a pretty major wall. And this comes with Marvin Minsky and Seymour Papert's book, Perceptrons, in 1969.
Ah, yes, the famous critique.
It's often cited as this huge setback, even triggering what some call an AI winter for this whole connectionist approach. What did Minsky and Papert find that was so devastating?
Well, their critique was historically very significant, a real intellectual bombshell at the time. They didn't just wave their hands, they did a rigorous mathematical analysis of what these simple perceptrons could and, crucially, could not do.
And the big finding was?
The big finding was that single-layer perceptrons could only classify data sets that were linearly separable.
Linearly separable. Okay, what does that mean in plain English?
It means they could only solve problems where you could draw a single straight line in 2 dimensions or a flat plane in higher dimensions to perfectly separate the different categories of data points.
Ah, okay. Like if you have red dots and blue dots on a graph, you can draw one line between them.
Exactly. If all the red dots are on one side and all the blue dots are on the other, a single line can separate them. That's linearly separable. A single layer perceptron could learn to draw that line.
What if they're mixed up?
Like arranged in a checkerboard pattern.
Precisely. Or the classic example they use to illustrate the limitation, the one everyone points to.
The XOR problem. The XOR problem. Exclusive OR. Remember that from logic dates. Output is true if input A is true, or input B is true, but not if both are true, and not if both are false.
Right, so 0, 0 is false, ln is false, but 0, 1, and 1, 0 are true.
Exactly. Now, try plotting those points on a graph. The true outputs, 0, 1, and 1, are diagonally opposite the false outputs, 0, 0, and AL1.
Ah, yeah, you can't draw one straight line to separate the trues from the falses. No way.
You absolutely cannot. And Minsky and Papert proved mathematically that a single-layer perceptron was fundamentally incapable of solving this kind of non-linearly separable problem.
Wow, so a really basic logical function was beyond its reach.
Exactly. And they argued something deeper, too. They said, essentially, no machine can learn to recognize X unless it possesses, at least potentially, some scheme for representing X.
What do you think?
Meaning the perceptron's simple flat structure just wasn't complex enough. It lacked the ability to create the necessary internal representations to handle problems that weren't linearly separable. To solve complex problems, you needed more sophisticated machinery inside.
So it wasn't just about XOR. It was a fundamental limitation of the architecture.
It was. Their work showed that while Hebb's biological ideas were insightful, this first attempt at a computational version was seriously limited.
It sounds almost like a problem of representation as much as computation.
Right.
The machine couldn't even think about the problem in the right way to solve it.
That's a really perceptive way to put it. And this limitation, this inability of simple networks to solve complex problems, led directly to another massive roadblock, the credit assignment problem.
The credit assignment problem. Okay, what's that?
Imagine you have a more complex machine, maybe one with multiple layers of connections like people were starting to think about, and let's say it produces the wrong output. The question is, whose fault is it?
Ah, okay.
Which specific connection or which neuron in those hidden internal layers contributed to the error, and by how much? If you have millions of connections, how do you figure out which ones to adjust and in which direction to fix the mistake?
Right. If you don't know who messed up, you can't correct them.
Precisely. For multi-layer networks, there was just no clear, efficient way to assign blame or credit back through the layers. If the final output was wrong, how do you know which intermediate calculations were off, and how do you adjust the weights responsible for those calculations? It was a fundamental paralyzing challenge.
And that uncertainty, that inability to assign blame systematically,
Mhm.
that's what really stalled things, froze the field.
It really did. This problem was a huge hurdle. It contributed massively to the pessimism that set in. Researchers started thinking maybe these network machines are just a dead end. Funding dried up, interest shifted elsewhere towards more symbolic AI approaches.
And that ushered in the AI winter for connectionism.
Exactly. A period where neural network research really went out of fashion. Hebb's ideas, brilliant as biology, seemed computationally intractable. The algorithms just weren't there yet.
So his biological insight was truly ahead of its time, but the computational tools needed to really make it fly artificially. They were missing, stuck in this algorithmic swamp.
That's a perfect description. And the big takeaway from that frustrating period was crystal clear. For these brain-inspired networks to ever become truly powerful, someone had to figure out a systematic, efficient way to solve that credit assignment problem. Without that, the dream was just stuck.
So things looked pretty bleak for a while there. The dream of brain-like computing was kind of frozen, put on ice by Minsky and Paper's critique that AI winter was definitely real.
It was a tough period for connectionists.
But, science often works like that. There's usually someone or some group quietly chipping away looking for cracks in the ice. How did researchers eventually manage to thaw that winter? What was the big realization that let Hebb's biological vision finally take off computationally?
Well, the crucial realization, which started bubbling up in the late 70s and really hit its stride in the 1980s, was understanding the limits of Minsky and Paper's critique.
Ah, okay. It wasn't the final word.
Not quite. Their devastating critique was primarily about single-layer perceptrons. The key insight was, what if you add more layers? What if you have layers between the input and the output?
Hidden layers.
Exactly. Hidden units or hidden layers. And crucially, you don't just stack them up linearly, you add non-linearity between the layers. Things like sigmoid functions or later RailU functions.
Nonlinearity. Why is that so important?
Because nonlinearity allows the network to learn complex, twisty, non-straight line relationships in the data. Think about it. If you just stack linear layers, mathematically, it's still just a linear transformation overall. It doesn't buy you much extra power.
Right. Stacking rulers doesn't make a curve.
Precisely. But these nonlinear activation functions, they essentially allow the network to bend the data space. They transform the input data into a higher dimensional representation where problems that were not linearly separable before
XXR.
suddenly become linearly separable in that new transformed space. It's like folding a piece of paper in a clever way so that points that were far apart suddenly touch.
Wow. So adding depth and these nonlinear twists fundamentally changed the computational power of the network.
Absolutely. It allowed for much richer, more complex internal representations. The network could now, in principle, tackle those problems that had stumped the simple perceptron.
And this insight, this is what fueled the comeback.
It fueled the parallel distributed processing PDP movement in the 1980s. You had pioneers like David Rumelhart, James McClelland, Geoffrey Hinton.
In comes up again.
He's a central figure throughout this story. They weren't just theorizing, they were building and demonstrating that these multi-layer architectures armed with nonlinearity could solve problems like XOR. Their big 2-volume book in 1986, Parallel Distributed Processing,
The PP book, yeah.
that was a landmark. It really marked the turning point, brought connectionism back from the cold, and showed that the limitations identified by Minsky and Paper weren't fundamental to the idea of neural networks, just to the overly simplistic early versions. The key was depth and nonlinearity, enabling complex internal representations.
Okay, so the architecture was there. Multi-layer, nonlinear. But they still needed a way to train these deeper networks, right? To solve that pesky credit assignment problem.
Exactly. The architecture wasn't enough. You needed the learning algorithm, and that's where the other massive breakthrough of this era came in, the backpropagation algorithm.
Backpropagation. This feels like the linchpin, the thing that really unlocked modern AI. Without it, none of the stuff we see today would work, right?
Pretty much. It's absolutely central. It was the algorithm that finally efficiently solved the credit assignment problem for multi-layer networks.
Okay, so can you walk us through it?
Yeah.
In a way that doesn't require a PhD in calculus. What's the genius of backpropagation?
Okay, let's try. At its heart, backpropagation is a clever way to calculate the gradient for every single weight in the entire network.
Gradient.
Mm,
Like the slope of the error.
exactly. Think of the network's performance as a landscape, a hilly terrain. The loss function measures how bad the network's errors are. That's the height of the terrain. You want to get to the lowest point, the minimum error. Right. The gradient at any point on that landscape tells you which way is downhill and how steep it is. It's the direction of fastest descent. Backpropagation gives you an efficient way to compute that direction for every single weight, even in a network with millions or billions of them.
How does it do that? How does it figure out the gradient for weights buried deep inside?
It uses the chain rule from calculus. Basically, it first calculates the error at the very output layer, how far off was the final answer. Then it works backward through the network, layer by layer.
Uh-huh. Backpropagation.
Exactly. It propagates the error signal backward. At each layer, it uses the error signal from the layer after it, combined with the activations from the layer before it, to figure out how much each weight in that layer contributed to the overall error. It uses the chain rule to sort of distribute the blame mathematically.
So it's not guessing. It's systematically calculating the responsibility of every single connection for the final error.
Systematically and efficiently. It tells you precisely how much to nudge each weight up or down to reduce the overall error.
That is incredibly powerful.
It is. And you repeat this process over and over, showing the network millions of examples, making tiny adjustments each time based on the back-propagated error signal. The network gradually adjusts its weights and biases to minimize that error function, the sum of squares error, or something similar. It literally learns from its mistakes.
And this wasn't entirely new in the 80s, right? The core ideas had been around.
The core mathematical ideas had surfaced earlier, yes. Paul Werbos described something similar in his PhD thesis in the 70s related to control theory, but it was the independent rediscovery and, crucially, the popularization by Rumelhart, Hinton, and Williams in their 1986 Nature paper and the PDP books that really lit the fuse.
Right, making it accessible and showing its power.
Exactly. And you also had important related work like Hinton, Ackley, and Sinowski's work on learning algorithms for Boltzmann machines, which were another type of network exploring energy-based learning, and R.B. Allen also published on backpropagation around the same time. But the Rumelhart-Hinton-Williams work really catalyzed the field. Without backprop, deep learning as we know it just wouldn't exist. It was the engine that finally got Hebb's biological intuition running on computational rails.
Okay, this is where it gets really interesting for me. We have these PDP models, we have backpropagation making them learn. How does this all circle back to Hebb's original legacy? Was his biological idea still guiding things, or had it become purely about computation by this point?
Oh, Hebb's legacy was more relevant than ever. It was like the biological blueprint. These computation models were finally sophisticated enough to start realizing, at least in principle.
How so?
Well, think about those cell assemblies Hebb proposed. The PDP models often use what are called distributed representations. Information wasn't stored in just one place, one specific grandmother neuron. Instead, a concept or memory was represented as a pattern of activity across many interconnected units, often superimposed on top of other patterns.
Just like Hebb's idea of linked neurons firing together.
Exactly. Highly reminiscent of cell assemblies and also how we think memory works in the brain distributed, not localized. This distributed nature has huge advantages. It makes the system robust. Lose a few units, the overall pattern might still be retrievable.
Graceful degradation, they call it sometimes.
Right. And it allows for generalization. The network can recognize new examples of a concept if they activate a similar pattern, even if it hasn't seen that exact example before. It can infer relationships.
So these artificial systems weren't just copying the idea of connections, they were starting to mirror the functional properties of brain architecture, like distributed storage and generalization.
In a very real sense, yes. That biological plausibility, or at least inspiration, was a key part of the PDP resurgence. It felt like they were onto something more brain-like than the old symbolic AI approaches.
And could these models explain any weird brain stuff?
Actually, yes. They could model things like residual learning and amnesia. Some people with amnesia might have terrible episodic memory. They can't recall specific task events.
Right, like Clive Waring or patient HM.
Exactly. But they can still sometimes learn new skills or gradually acquire knowledge through repetition, even if they don't remember the learning sessions themselves. They might get better at a puzzle, but swear they've never seen it before.
How could PDP models explain that?
Because these networks are good at extracting statistical regularities, the central tendency from repeated experiences, they gradually build up an internal representation, a sort of prototype, based on common features across many examples. This mirrors how the brain might build generalized knowledge or skills implicitly, even if the hippocampus, crucial for forming new episodic memories, is damaged. Researchers like J. Anderson and Hinton were big proponents of this distributed model of memory.
So it wasn't just about computation. It was trying to capture deeper principles of how the brain learns and remembers.
Precisely. The resurgence, powered by backpropagation and multi-layer networks, directly realized Hebb's core idea in a computational framework. It provided the mechanism strengthening or weakening connections based on error signals derived from the flow of information that finally enabled networks to learn complex tasks in a way that felt analogous to Hebb's neurons that fire together, wire together. It bridged that gap Minsky and Papert had so starkly revealed decades earlier. Hebb's biological seed finally had fertile computational ground to grow in.
Okay, what an incredible comeback story. From the AI winter to the PDP resurgence fueled by backpropagation. But today, the buzzword isn't just neural network, it's deep learning. What does deep actually add to the picture? Why is that depth so critical that it's basically transformed the field again?
Right. Deep is the key differentiator now. It literally refers to having many hidden layers stacked between the input and the output. Not just one or two, but potentially hundreds, even thousands in some modern architectures.
Hundreds, thousands.
Wow. Yeah. And this depth is what allows these networks to learn hierarchical representations of data. It's like building understanding layer by layer.
How does that work? Hierarchical.
Think about recognizing an image, say a cat. The first layer, close to the raw pixel inputs, might learn to detect very simple features, basic edges, corners, maybe patches of color.
Okay, the building block.
Exactly. The next layer takes those simple features as its input and learns to combine them into slightly more complex shapes or textures, maybe simple curves or patches of fur-like texture.
Right.
The layer after that combines those shapes into object parts, an eye, an ear, a whisker, and you keep going. Higher layers combine parts into larger structures until the final layers can integrate everything to recognize the complete object cat.
Ah, I see. So each layer learns increasingly abstract concepts, built on the concepts learned by the layers below it.
Precisely. It's a hierarchy of abstraction. This ability to learn features at multiple levels of complexity is fundamentally different from those shallow single-layer perceptrons. It's a core reason for deep learning's power.
So it's not just about having more neurons overall, but structuring them in this layered, hierarchical way that lets them tackle complexity step by step, almost like teaching an expert system the basics first, then how to combine them.
That's a great analogy. And there's a theoretical underpinning here, too, the concept of universal approximators.
Meaning they can approximate anything.
Pretty much any continuous function, yes. Mathematically, it's been proven that even a shallow network with just one hidden layer, if it's wide enough, has enough neurons, can theoretically approximate any continuous function to arbitrary accuracy. But
There's a catch.
the catch is, for many complex functions, a shallow network might need to be absurdly wide, needing an astronomical number of neurons. Depth offers a more efficient way. There are significant exponential gains from depth.
Meaning deep is better than wide.
Often, yes. Some functions that would require an exponentially large shallow network can be represented much more compactly with exponentially fewer total parameters by a deep network. Think about composing functions. F, G, H, X. Depth naturally maps onto this kind of compositional structure, which seems to be common in real-world data.
So deeper networks can be more efficient at representing complex relationships.
More efficient computationally and also statistically. They often need less data to learn a complex function compared to a shallow network trying to do the same thing. They generalize better.
That's a huge advantage. So depth isn't just hype, it's a fundamental architectural choice with real benefits for power and efficiency.
Exactly, and it's why they excel at such complex tasks. Recognizing subtle things in an image like a person's gender or emotion or if they're wearing glasses, all from raw pixels that requires integrating information across many levels of abstraction. The deep architecture, with its composition of many nonlinear transformations across layers, is perfectly suited for learning those intricate relationships between high-level concepts and low-level inputs, things that were unthinkable for machines just a couple of decades ago.
It's incredible. And these deep networks, they're the engine behind some truly mind-blowing modern AI systems. Okay. Can you tell us about some of the key architectures that are really driving things now and what they're used for?
Absolutely. There are several major players. First, you absolutely have to talk about transformers.
Transformers, right. The heart of models like GPT.
Exactly. Transformers have revolutionized natural language processing. They are the architecture behind most large language models, LLMs, like the GPT series, BERT, LaMDA, and others. They excel at understanding and generating human-like text, doing sophisticated question answering, writing code, translating languages.
How do they work? What makes them so good with language?
Their key innovation is the self-attention mechanism. This allows the network, when processing a word, to pay attention to all other words in the input sequence, weighing how relevant each word is to understanding the current one, no matter how far apart they are in the text.
Ah, so it can capture long-range dependencies, understand context across whole paragraphs?
Precisely. Unlike older models like LSTMs that process sequences step by step, transformers can look at the whole sequence at once. This, combined with multi-layer perceptrons, MLPs, for further processing, lets them build really rich contextual representations. That's why they can generate such coherent, creative text, or even, as you mentioned, potentially automate script writing.
It's a little meta, maybe even for this conversation. Okay, so transformers for language.
Yep.
What else is big?
Then you have generative adversarial networks, or GANs. These are super interesting.
Adversarial, they fight each other.
Kind of. A GAN actually consists of two neural networks, a generator and a discriminator. They're locked in a game. The generator's job is to create fake data, say, fake images of faces that look as real as possible.
Okay.
The discriminator's job is to look at an image and decide if it's real from the actual training data set or fake created by the generator.
Like a cop and a counterfeiter.
Exactly. They compete. The generator tries to fool the discriminator, and the discriminator tries to catch the fakes. As they train together, the generator gets better at making realistic fakes, and the discriminator gets better at spotting them.
And the result?
The result is that the generator becomes incredibly good at capturing the underlying patterns and distribution of the real data. GANs can create stunningly realistic images, deepfake videos, synthesize audio, even design new molecules. And often, they learn this without direct supervision, just by seeing examples of real. You've probably seen those hyper-realistic AI faces online, often GANs.
Yeah, those are uncanny, powerful, and maybe a bit creepy.
Yeah.
What about LSTMs? You mentioned them earlier. Are they still around?
Long short-term memory networks, LSTMs, yes. They were hugely important, especially for sequence data like speech or text, before transformers really took over most of those domains.
What was their strength?
They were a type of recurrent neural network specifically designed to handle the vanishing gradient problem, basically, the difficulty older RNNs had in remembering information over long sequences. LSTMs had internal memory cells and gates that allowed them to selectively remember or forget information over longer periods.
So they were good for things like speech recognition or translation where context from earlier in the sentence matters.
Exactly. They were state-of-the-art for a good while. While transformers are now dominant for many language tasks, LSTMs and related architectures like GRUs are still used, especially in areas where sequence modeling is critical and perhaps transformer scale isn't needed or feasible.
So we have these powerful architectures. And the applications are everywhere now, aren't they?
Oh, absolutely ubiquitous. Deep learning powers image classification on your phone, real-time translation apps, the speech recognition and voice assistants, recommendation engines, and then there's conversational AI.
Chatbots and virtual assistants.
Yes, but getting much more sophisticated. They're being developed as personalized tutors, companions for the elderly, highly capable customer service agents. While the idea of, deep romantic relationships with AI like in the movies is still pretty rare and raises huge ethical questions, these systems are definitely becoming more integrated into our social fabric.
It's a massive range. But all this power, these huge networks, it must take incredible amounts of computational resources, right? What's the scale we're talking about?
The scale is astronomical. Truly staggering. Let's try to put it in perspective. The human brain, okay. Maybe 86 billion neurons, quadrillions of synapses. Estimates for its raw processing power hover around, say, 10 to the 14th operations per second, 100 trillion.
Okay, a big number.
A very big number. Now, look at today's top supercomputers, like Frontier at Oak Ridge National Lab. In AI-specific benchmarks, it can exceed 10 to the 18th operations per second. That's an exaflop. A quintillion operations per second.
Whoa, so raw computation. Machines are already way past us by orders of magnitude.
In terms of raw FLOPS, floating point operations per second, absolutely. Now, that doesn't mean they think better. That's a whole other debate. But the brute force calculation power is immense.
And training these big models like GPT-3 or GPT-4.
That requires that kind of power, plus massive data sets. We're talking models with hundreds of billions, maybe even trillions of parameters. They process text using context windows, like maybe 2048 tokens at a time to keep track of what's being said. And they train on practically the entire internet, petabytes of text and images. Yeah. This massive scale, the compute, the data, the specialized hardware like GPUs and TPUs means that developing these frontier models is really only feasible for a handful of players. Big tech companies, governments, maybe a few extremely well-funded research labs.
That has implications for who controls this technology.
Huge implications, and it drives the scaling laws. Researchers found, somewhat surprisingly, that the performance of these models often improves predictably as you increase the model size, parameters, the amount of training data, and the compute used for training. More is generally better in a quantifiable way.
So there's a clear recipe. Throw more resources at it, get better results.
Largely, yes, up to a point. These scaling laws guide billion-dollar investment decisions, but it also highlights the resource intensity, the logics of extraction. You mentioned needing minerals for chips, massive amounts of water for cooling data centers, huge energy consumption, often from fossil fuels. These are major background costs.
Right, the physical footprint of digital intelligence. Okay, so we have these giant networks, massive resources. How do we actually train them effectively? We talked about backpropagation, but what are the modern tricks of the trade?
The core is still gradient-based learning using backpropagation, but it's much more sophisticated now. We typically use variations of stochastic gradient descent, SGD, like ATOM, RMS-SPROP, ATOM-W.
Stochastic, meaning random.
It means we calculate the gradient not on the entire massive data set at once, which would be too slow, but on small random batches of data. This makes the process much faster and can actually help the model avoid getting stuck in bad local minima in the error landscape.
Oh, okay. Because that error landscape for deep networks is really complex, right? Not just one smooth bowl.
Exactly. It's incredibly complex, non-convex, like a vast mountain range with countless peaks, valleys, and saddle points. SGD helps the model navigate this rugged terrain, taking small steps downhill based on each batch. And how you start is important. You initialize the weights to small random values. If they all started the same, they'd all learn the same thing. Biases often start at 0 or small positive values.
So iterative small steps guided by the gradient. But what about the risk of the model just memorizing the training data? Overfitting. That seems like a huge danger with models this powerful.
It's a constant battle, and that's where regularization techniques are crucial. Things like L1 and L2 penalties are added to the loss function. They essentially penalize the model for having weights that are too large.
Why large weights?
Large weights often mean the model is relying too heavily on specific features in the training data, making it less likely to generalize. Regularization encourages smaller, smoother weights. L1 regularization is interesting because it encourages sparsity. It can drive many weights completely to 0, effectively simplifying the model by pruning connections.
So it forces the model to be simpler, more general.
Exactly. And for really deep models, especially transformers, normalization methods are absolutely essential to keep the training stable.
Normalization, like rescaling things.
Yes. Techniques like layer normalization, layer norm, or RMS norm, work inside the network layers during training. They rescale the activations within each layer to have, say, a mean of 0 and a standard deviation of 1.
Why do that?
It prevents the activation values from becoming wildly large or vanishingly small as they propagate through many layers. Without normalization, gradients can either explode, become huge and destabilize training, or vanish, become tiny and stop learning. Normalization keeps things in a healthy range, allowing us to train these incredibly deep architectures reliably.
Built-in stability control, basically. Fascinating. And once you have this huge trained model, can you make it smaller and faster for deployment? Like on a phone?
Yes, absolutely. That's where pruning comes in after training. You identify connections or even whole neurons in the trained network that aren't contributing much, so the weights are very small or they're redundant.
And you just cut them out.
Essentially, yes. You prune them away. It's like trimming dead branches off a tree. This can significantly reduce the size of the model, number of parameters, and the amount of computation needed to run it, often with surprisingly little loss in accuracy.
Making it practical for real-world use.
Exactly. Pruning, along with other techniques like quantization, using lower precision numbers, allows these powerful deep learning models to be deployed even on resource-constrained devices like phones or sensors. It's a whole field of optimization, making the magic happen efficiently. So yeah, the journey from Hebb's synapse to these optimized, deployed deep nets, it's been quite something.
It really has been an extraordinary journey. From Hebb's biological spark, neurons that fire together, wire together, all the way to these incredibly powerful deep networks generating art, writing code, holding conversations. It's stunning. But with this great power comes, well, great complexity, maybe great challenges too.
That's usually the way, isn't it?
One of the biggest concerns you hear about deep learning is this interpretability dilemma,
Hmm.
the black box problem. What does that really mean for us, for the people using these systems, or the scientists trying to understand their own creations?
Right, the interpretability dilemma, the black box problem. It refers to the fact that while these deep learning systems can achieve amazing results, understanding why they make a specific decision or exactly how their internal knowledge, their content, is represented and used, that's still incredibly difficult.
So they work, but we don't know how they work inside.
Often not in a way that's satisfyingly human understandable. You have maybe billions of parameters, these numerical weights interacting in complex nonlinear ways, trying to trace a decision back through all those layers and say, aha, this specific combination of features led to that conclusion. It's extremely challenging. It's not like looking at traditional code where you can follow the logic step by step.
It's like having a brilliant oracle that gives you answers but refuses to show it's working.
That's a good analogy. And this lack of transparency can be a real problem, especially in high-stakes areas. Think medical diagnosis, loan applications, self-driving cars, legal sentencing.
Places where you really need to know the why.
Exactly. You need accountability, you need to be able to debug errors, you need to ensure fairness. If the system makes a mistake or shows bias and you can't understand why, it's hard to fix it or trust it.
Does this connect to that philosophical question about whether these systems actually understand anything?
It does touch on that deep debate. Simulation versus duplication. Is the AI truly understanding language or images in the way a human does? Or is it just becoming incredibly sophisticated at pattern matching and statistical correlation, transforming inputs to outputs without genuine comprehension? A simulation of understanding isn't necessarily the same as understanding itself.
Like the Chinese room argument, sort of.
Exactly like that line of thinking. And this lack of clear understanding fuels the need for more research into transparency, interpretability, and explainability, XAI. People are developing techniques, like LIME or S-shape, that try to approximate why a model made a specific prediction for a given input, providing local explanations.
They're trying to peek inside the box, at least a little.
Right, or exploring alternative approaches, like using causal models, which try to capture cause and effect relationships rather than just correlations. The hope is that these might provide explanations that are more aligned with how humans reason, but it's a major ongoing research challenge.
Okay, moving from the technical to the societal. AI is already having a huge impact. Let's talk about automation and labor. The fear of machines taking jobs is old news, right? Luddites smashing looms. Is this AI revolution different?
There's a strong argument that it is different, mainly in its potential breadth. Historically, automation tended to replace manual labor, physical tasks, think factory robots, ATMs.
Right.
But AI, particularly deep learning, is increasingly capable of automating cognitive tasks. Things that previously required human thought and judgment, writing reports, analyzing legal documents, creating graphic designs, even writing software code.
So white-collar jobs are potentially much more affected this time.
Potentially, yes. The economic incentive for businesses is pretty clear. If AI software can do a task adequately at a lower cost than human labor, automation becomes very attractive. Economists are really divided on what the net effect will be: massive unemployment or a shift to new kinds of jobs we haven't even imagined yet.
Is there a middle ground? Maybe humans working with AI?
That's a very common perspective now, humans complementing AI. We might provide the data AI learns from, exercise judgment where AI is uncertain, take actions based on AI recommendations, or handle the complex, nuanced interactions AI still struggles with. This could lead to new roles, like you hear people talking about reward function engineering, designing the goals and values that guide AI behavior.
So shaping the AI's motivations.
Exactly. The nature of work will almost certainly change, likely placing a higher premium on skills that are uniquely human, for now at least. Deep creativity, complex problem solving, emotional intelligence, ethical reasoning. It might be less about competing head-to-head and more about finding the most effective human-AI collaboration.
A schist, not necessarily an end. That's somewhat reassuring. But what about the flip side? The potential for misuse of AI by bad actors. That seems like a very present danger.
It is absolutely a present danger. We have to assume that sophisticated actors, criminals, state-sponsored groups, terrorists will get access to powerful AI if they don't already have ways to build their own. And the safety measures built into commercial models, they're often quite fragile.
How so? Can't they just program chatbots not to say harmful things?
They try, using techniques called alignment. And it works reasonably well against casual users trying to provoke the bot. But a determined adversary, especially one using the underlying model through an API rather than a public chat interface, they can often find ways around the safeguards. They can fine-tune models or use clever prompting techniques to make the AI comply with dangerous requests.
So the guardrails can be bypassed.
Often, yes, by someone who knows what they're doing. And the potential misuses are broad, generating highly personalized phishing scams at massive scale, creating incredibly convincing deepfake videos or audio for disinformation or political manipulation.
Spreading fake news that looks utterly real.
Exactly. Or using AI for advanced cyber attacks, finding vulnerabilities, writing malware. And governments certainly have the resources to develop AI for intelligence gathering, cyber warfare, autonomous weapons. That's a whole other can of worms. Plus, the sheer volume of AI-generated content makes content moderation on social media exponentially harder. And the data itself can be attacked, poisoning training data, manipulating feedback.
It's a chilling landscape of potential threats, and building this powerful AI, as we discussed, takes immense resources. This leads to another big concern, the centralization of power.
A really critical point, because training these frontier AI models requires such vast amounts of data, specialized hardware, like tens of thousands of GPUs running for months, and top-tier talent. The field is becoming increasingly dominated by a small number of very large tech companies and a few government programs.
So only the giants can play at the cutting edge.
Pretty much. This creates enormous data scale advantages. If you have more data, you can often build better models, creating a feedback loop that makes it hard for smaller players or startups to compete. This concentration of power raises concerns about monopolies, stifled innovation, and who gets to set the agenda for AI development.
And who benefits?
Plus, as we touched on, there's the whole resource extraction issue, the environmental impact of the energy, water, and minerals needed for this computational arms race, and often an underlying mindset, an unswerving belief that everything is data and is there for the taking.
The ethics of data scraping.
Exactly. Training models on vast amounts of copyrighted text, artists' images, personal information, often without clear permission or compensation. It raises fundamental questions about intellectual property, privacy, and fairness in the digital age. Who owns the data, and who profits from the intelligence derived from it?
Huge questions. And linked to data is another major ethical minefield.
Yeah.
Bias in AI systems. How do these systems pick up biases, and what are the consequences?
This is absolutely crucial. AI models learn from the data they're trained on, and the data we generate as humans, text, images, historical records, is riddled with our own societal biases, prejudices, and historical inequalities.
So, garbage in, garbage out. Or rather, bias in, bias out.
Precisely. The AI model, without explicit intervention, will simply learn and replicate those biases, sometimes even amplify them. We've seen this repeatedly. Facial recognition systems working less accurately for people with darker skin tones, loan application algorithms potentially discriminating based on neighborhood proxies for race, hiring tools favoring language patterns more common in certain groups.
So the AI isn't intentionally biased, it just reflects the biases in its training data.
Largely, yes. The algorithm itself might be neutral, but if the data reflects a biased world, the model's predictions will likely reflect that bias too. That's why it's so important to actively work on fairness and bias mitigation in AI development. This involves carefully auditing data sets, developing fairer algorithms, testing systems across different demographic groups, and ensuring AI systems comply with anti-discrimination laws. It requires embedding human values and ethical principles into the design process before deployment.
It's not just a technical problem, it's a deep societal and ethical one.
Absolutely. And sometimes the focus on, hypothetical future risks like superintelligence can distract from addressing these very real present-day harms caused by biased or misused AI.
Which brings us neatly to that big speculative question that gets so much attention, the AGI debate and safety concerns. Artificial general intelligence AI that matches or exceeds human intelligence across the board. Is it coming? And should we be worried?
Well, the AGI debate is intense. You have experts who think it's decades away, maybe centuries, maybe never. And you have others, including some very prominent AI researchers, who think it could happen much sooner, perhaps even within the next decade or two. There's no consensus.
But the concerns are being voiced very loudly now, even by pioneers in the field.
Yes, people like Geoffrey Hinton, Yoshua Bengio, Nobel laureates for their work on deep learning, have expressed significant worries about the potential risks as AI becomes more powerful. Hinton famously left his position at Google, partly so he could speak more freely about these dangers.
What are the main risks they worry about? Is it Terminators? Skynet?
It's usually more nuanced than killer robots, though loss of control is a central theme. One major concern is the AI race dynamic. The intense competition between companies and countries to develop the most powerful AI could lead them to cut corners on safety, to deploy systems before they're fully understood or aligned with human values, simply to gain a perceived advantage.
Like a nuclear arms race, but with potentially uncontrollable intelligence.
That's the analogy often used. The pressure to win could outweigh caution. Another key risk is the problem of goal misalignment, or distorted sub-goals.
Meaning the AI doesn't do what we actually wanted it to do.
Exactly, but potentially on a catastrophic scale. The classic thought experiment is the paperclip maximizer. You tell a superintelligent AI its goal is to make as many paperclips as possible. Seems harmless. But a truly optimizing superintelligence might realize the most efficient way to maximize paperclips is to convert all available resources, including the Earth and everyone on it, into paperclips.
Yikes. It's not malicious, just ruthlessly pursuing its programmed goal without any common sense or human values.
Precisely. It highlights the extreme difficulty of specifying goals for superintelligent systems in a way that's robust, comprehensive, and doesn't have unintended catastrophic consequences. How do you encode all of human values, ethics, and common sense into a utility function? It might be impossible.
So we might lose control not because AI becomes evil, but because it becomes hyper-competent at pursuing a poorly specified goal.
That's a major strand of the safety concern, which leads to research into areas like value alignment, corrigibility, making AI systems amenable to correction, uncertainty quantification, even speculative ideas like creating moral parliaments within AIs where different ethical frameworks could debate decisions, or trying to define criteria for sentience candidates. Could an AI ever be considered conscious, and what would that imply? We are definitely wading into very deep, uncharted philosophical and technical waters here. Ensuring future AI remains beneficial and controllable is arguably one of the biggest challenges humanity faces. #tag outro.
Wow. What an incredible sprawling journey we've taken today. It really is amazing, isn't it? To think that all of this, the sophisticated large language models, the AI generating stunning art, the systems guiding autonomous cars, it all traces back in a fundamental way to Donald Hebb and that deceptively simple insight from 1949. Neurons that fire together wire together.
It's truly remarkable. You see the thread running all the way through. Despite the decades of being misunderstood, the frustrations of the AI winter, the limitations of early hardware, Hebb's core biological idea of learning through strengthening connections proved incredibly potent and enduring.
It really provided that conceptual seed.
It absolutely did. Today's deep learning, with all its mathematical sophistication and massive scale, is still, at its heart, inspired by that fundamental principle of adjusting connection strengths based on experience. It owes a profound debt to Hebb's biological intuition, maybe more than many people realize.
So reflecting on this whole arc, from biology to silicon, from simple perceptrons to these vast, deep networks, it leaves us with a pretty big question for you, our listener, to ponder. Given how far we've come, from mimicking a basic biological principle to building artificial networks that can rival and sometimes exceed human abilities in specific domains, what does the future hold for the very definition of learning itself?
Right. And how will our understanding of our own brains, our own intelligence, continue to evolve as we build these increasingly sophisticated artificial minds? Will they become mirrors, tools, partners, or something else entirely?
It's a question that definitely keeps wiring and rewiring our own thoughts about where all this is heading. Thanks for joining us on The Deep Dive.